What we're going to be doing is we've seen a few times where we have radicals in the denominators, and that's a big no-no in math. If we have a fraction that is unsimplified, like 2/4, we never leave it as 2/4. We always simplify it to what? 1/2, right? By dividing the numerator and denominator by the same value to reduce it as much as we can. The same is true for radicals in the sense that we never want to leave a radical in the denominator, or we never want a fraction with a denominator in a radical expression. And so we do what's called rationalizing the denominator, making it from a radical to something that doesn't have a radical. Okay? It's a similar process as simplifying a fraction, but instead of dividing, we're multiplying. Okay? And so let's take a look at our first set of examples. All of these have radicals in the denominator. Okay? And I don't want to leave them like that. So we look and say, all right, I need to multiply this by a fraction that equals 1. My goal is to make my denominator something where I can actually take the square root. So I want to multiply it by a radical of some kind. And the primary question becomes, what can I multiply 2 by so that it becomes a perfect square? By 2. Because if I multiply 2 by 2, I get 4. So I want to multiply the top and the bottom of my fraction by the square root of 2. So when I do the multiplication, I get the numerator will become what? The square root of 6. And the denominator becomes the square root of 4, allowing me to simplify it as the square root of 6 over 2. Okay? So we want to figure out what's going to complete that square so that I can go ahead and actually take the square root. Or if I have a third root or a fourth root, the idea is the same. What can I multiply by so that I can actually complete that radical and end up with a rational number in my denominator instead of an irrational number? Okay? When I'm looking at b, again, I want to multiply by the third root of something because I'm dealing with a third root. What can I multiply 9 by so that it becomes a perfect cube? By 3. Because what is 9 times 3? 27. And then 6 times the cube root of 3 is just 6 cube root of 3. So what is the cube root of 27? 3. Now, occasionally, once we rationalize, we'll also get something else that we can then simplify. 6 over 3 reduced. So then my final answer becomes 2 third root of 3. Now, when we have some radicals, we may want to make sure that we can simplify first. That just makes the whole process of rationalizing easier. I can rationalize it in the form that it is now, but simplifying is going to, in the front, is going to save you more simplification later. So, can I simplify the square root of 16? Yeah, what is the square root of 16? 4. Can I simplify the square root of 9x? 3 square root of x. Now the only thing I have to worry about rationalizing is the x, not the 9x. So I have 8, 3 root x. Now I need to multiply. What can I multiply x by so that it becomes a perfect square? The square root of x. So I have 8 square root of x over 3 square root of what? X to the second. So when I take the square root, I end up with 3x. So whether there's rational numbers or variables, it's the same thing. We're looking for that perfect square or that perfect cube. So what radical can I multiply it by so that I get that result, allowing me to remove the radical from the denominator? When you've got your fractions inside your radical, it's usually best to use your quotient rule and break it apart and see if you can simplify part of it further. Can I take the cube root of 1? Yes, 1. This is 1. Cube root of 1 is 1. Fourth root of 1 is 1. Square root of 1 is 1. 1's a magical number to take roots of. What can I multiply 2 by so that it becomes a cube? Cube root of 4 over the cube root of 4. What is the cube root of 8? So I have the cube root of 4 over 2. Okay, questions so far? I end up doing a lot of multiplication. Yeah.
So, A, the only thing we did simplify is
You're talking about where on A? The square root of 6 over 2. I can't simplify the square root of 6. So it just stays the square root of 6. And I can't reduce as a fraction something inside a radical symbol and something outside of a radical symbol. They have to be both out. Alright? So again, we're going to apply our quotient rule so that I have the square root of 7x over equals the square root of 3y. So what am I going to multiply by for this one? 3y squared by 3y. Multiply by 3, that gives me a 9. Multiply by y, that gives me a y squared. Okay? So I'm going to multiply those together. So what is the square root of 7x times the square root of 3y? Good. And then the square root of 3y times the square root of 3y. 9y squared, which allows me to then simplify to be 3y. When you've got square roots, you see that you kind of end up with this pattern of multiply it by itself, so I get my denominator. That's a pretty recurring pattern. It gets a little bit more complicated when we have cube roots, so just be aware of that. But if you see a pattern emerging, that's because there kind of is one. It's just not all inclusive. Okay, B looks pretty complicated to start. Can I simplify my numerator at all? No. Can I simplify the denominator at all?
Yes.
Yeah, I can. Can I take the fourth root of 81?
Yeah.
Mm-hmm. What is the fourth root of 81? Mm-hmm. Can I take the fourth root of y to the fifth? Okay, so I split it. So then when I take the fourth root of y to the fourth, what do I have? Just y. So left on the inside, I'll wind up at a third root. That's the fourth root. Now the only thing I have to rationalize is the fourth root of y. That's it. So what can I multiply by to get something that I can take the fourth root of? What do I need my exponent to be so that I can take the fourth root? 4, right? Or a multiple of 4. So what can I multiply y by so that I end up with y to the 4th? Y to the 3rd. If I multiply by y to the 3rd with y, that gives me y to the 4th. So now let's multiply. 4th root of x times the 4th root of y to the 3rd gives me what? Y to the 3rd. X, y to the 3rd. Good. 3y, still there. Okay. 4th root of y times 4th root of y to the 3rd. Y times y to the 3rd.
Y to the 4th?
Yeah. That was our goal, right? Said I wanted something that was y to the 4th. So I picked y to the third, so I get y to the fourth, so that I can simplify it to be just what? What is the fourth root of y to the fourth? Y. So it just gives me 3y squared. You'll find it to be very repetitive after a while. Now I'm showing some of these steps in excess. Honestly, that once you become a little more proficient, you may not even have to show me this step. You can go from here to here. So it's just up to you. It's how comfortable you are. If you like to see that as the fourth root of y to the fourth and then simplify it, then go for it. But if you're more comfortable just recognizing that, oh, that's going to give me y to the fourth. When I take the fourth root, I end up with y. That's fine. Not going to be that nitpicky. Just depends on your comfort level. Okay? Now, we have two ways of rationalizing. That was when we have one term in our denominator. Okay? There was one radical expression. Sometimes we have two terms. They both may or may not have radicals in them. Okay? So when we have two terms, it's a different method called multiplying by the conjugate. Remember yesterday I talked about the conjugate special product. The radical went away when we multiplied conjugate expressions. The numbers are the same terms, but opposite operation. So we have the square root of 5 minus 1. And its conjugate would be the square root of 5 plus 1. That didn't change. That didn't change. The only thing that changed was the plus sign and the minus sign. And that was it. So when we multiply by conjugates, it gets rid of our denominator. Or I'm sorry, it didn't get rid of the denominator. It gets rid of the radical in the denominator, allowing us to rationalize. So we're going to do the same process of multiplying the numerator and denominator by the same thing. But instead of saying, okay, well, what will make it a perfect square? We know what's going to make it a perfect square. It's conjugate. Okay, so that's when we need to switch the sign. So make sure you keep those two distinct processes different. If it's one term, then you're picking what to multiply by to complete the radical. But if it's two terms, then we use the conjugate. So I'm going to leave 3 root 5, but I'm going to change the plus to a minus, and I'm going to leave the 1. And I'm going to do that same thing on the top. Okay? Always based on what the denominator is. Here we just do our distributive property. 3 times 3 root 5. 9 root 5. 3 times negative 1. Good. 3 root 5 times 3 root 5. 9 root 25. 3 root 5 times negative 1. And then 1 times 3 root 5. And then 1 times negative 1. And made it bigger, but it's going to become a lot easier because what is that? That cancels out. And then what's the square root of 25? What's 9 times 5? Minus 1. 40. Square root of 25 is 5. Multiplied it by the 9 to get 45. Subtracted that 1 to get 44. The denominator, done. What's my conjugate for the second one going to be? The denominator. Square root of 5 plus square root of 3. It's always based on the denominator because I'm rationalizing the denominator. That's what I care about getting rid of the radical. So I need to multiply by its conjugate. Okay? Now, when we're multiplying by conjugates, we get a little bit of a shortcut. Because I know that when I do my second and third multiplication, that gives me these two terms. They're going to cancel out. Those two terms I don't need. Okay? So I do the first multiplication, and I get what? square root of 25. Okay? And I know, because I'm multiplying by a conjugate, that when I do that multiplication and that multiplication, they're going to cancel. So I only need to do the first one and the last one. What's the negative square root of 3 times the square root of 3? Negative square root of 9. Those are the only ones I need to do because I know that root 5 times root 3 and negative 3 times root 5 are going to cancel. That's the whole point of the conjugates. I know those two are going to cancel. So it's like pretty formulaic. I can just do the first and the last. Numerator, you have to do the full distributive property. Okay, so don't skip that part. Root 6 times root 5. Root 30. Root 6 times root 3. 2 times root 5. And there you go. 2 root 3. Okay, so do the full distributive property of the numerator. But when you're multiplying by conjugates, you only need to do the first and the last because those are the only ones that are going to make a difference. Okay? Simplify the denominator first. What's the square root of 25? 5. Square root of 9. Okay, so 5 minus 3 giving me what? 2. Can I simplify any of these in the numerator? Which one? Square root of 18 simplifies to what? Let's break it apart first. What are my factors of 18? 9 and 2. Because I want the perfect squares, right? Okay. So I can square root that in just a moment. Can I simplify the square root of 30? Give me a factor of 30 that's a perfect square. Nope, can't. None of those are perfect square factors. Okay, so we're going to leave it as square root of 30. Square root of 9 times 2 becomes 3 root 2. Okay, 2 root 5. And 2 root 3. Can I add any of those in the numerator? Are the radicands the same on those? They have to have the same radicand. Oh, no. None of those have the same radicand. So that's it. Numerator got pretty ugly, but at least we rationalized it. Go ahead and try the third one on your own. Give that one a shot. Okay. Cube root of 3 plus 2 over the cube root of, let's say square root. Square root of 2 plus square root of 3. Your conjugate of root 2 minus root 3 on the numerator and denominator. Do your distributive property. You're going to end up with 4 terms in your numerator. The only one you can simplify is the square root of 9. When I multiply root 2 times root 2 and root 3 times negative root 3, I get root 4 minus root 9. So 2 minus 3 to give me negative 1. If I just have a negative 1 in the denominator, a negative number is fine. But I don't want to keep that negative 1 because that fraction is kind of superfluous. So what I do is just distribute the negative to all of the terms in the numerator, which is switching all of those signs. Okay? So if you have a negative 1, get rid of the negative 1, switch all the signs in the numerator, and then you can call it a day. There's nothing in the numerator that can be added because I don't have any like radicands, so I end up with that 4-term expression. added 2 more examples in so that we have some variables with our conjugates. It's the same process. What's my conjugate for this first denominator? It's the root m. Okay. Over, 3 root m minus root m. Okay. So let's do our distributive property. First one. Okay. Second one. Okay. Denominator. Good. These 2 I can skip because I know they'll cancel. So the last one. Negative square root of m squared. Okay. Can I simplify anything in the numerator? Yeah, so I can't subtract them. Are there any radicals I can simplify them?
6 and 9.
Square root of m squared. Simplify that one. Okay. What about the denominator? The 9's not inside the radical. 9x minus n. Okay. Conjugate for the last one. Okay. First multiplication. Second one. Denominator. Okay. Skip, skip. Last one. Okay. Can I simplify anything in the numerator? Anything in the denominator? Six x minus 3 root xy over 4x minus y. Ta-da!
So the outside just doesn't change.
Yeah, because it's not in the radical. So we're just square rooting what is in the radical, and what's outside stays outside. No change. Okay? Any other questions? It does become very repetitive. Okay? So once you get the pattern down, well, then it's just a matter of making sure you multiply correctly. Okay? So